Hey, what's going on YouTube? It's Alex here. Today, I'm going to talk about quantum computing theory, and hopefully I'll be able to explain like the basics of it and kind of make up for a lot of the explanations I've seen online that were just really unsatisfying for me when I was trying to learn this stuff. So quick background, I actually took a course called Intro to Theory of Quantum Computation back in like spring of 2020. I had moments of very deep regret in taking that class, but eventually I did make it out with a B, so that was pretty good. But enough rambling about me taking a class. Let's get into the actual video. So in order to establish an anchor point, I'm going to quickly review classical computational theory. So the whole point of digital technology is that computers do everything that they do by manipulating numbers, basically. So a good way to illustrate this is look at our number system, and I'm going to have a bunch of numbers just incrementing on the screen here. And think about the way that these numbers will increment. We only have 10 different symbols to represent a single digit in one of our numbers. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Once we get past the symbol 9 for a single digit, we have to go ahead, wrap back around to 0, and then increment the next digit by 1. So think about going from the number 9 to the number 10. We wrap back around to 0, and then the next place increments from a 0 to a 1. Now, there's nothing innately special about that number that comes after 9. It's just that we who decided upon this number system, we were like, okay, we were probably like, this is how many fingers we have, so it makes sense for us to have that many symbols, 0 through 9. And then once you get to like the number 10, that's a special number, we're going to go ahead and wrap back around to 0 and increment the next space. We just as easily could have chosen, say, like 5 to be that special number. We could have chosen like 20, in which case we'd have like an extra 10 symbols on our number system. You can also choose a really weird number, like maybe 13, if you really wanted to. And then these number systems would be known as base 5, base 20, or base 13, respectively. And our number system is known as base 10. So for classical computers, we use what's known as a base 2 number system, which is also called binary. And we do this because we have our classical computers running on electricity, because that is a very easily manipulable form of like energy. And there's a very easy way for us to represent two discrete states using electricity, and that's with high voltage versus low voltage. So in computational theory, we call this basic unit of information a bit. And that's because, again, it's in only one of two discrete states at a time, either you're 0 or you're 1. And then for actually computing stuff, we have what's known as logic gates. So logic gates, it's sort of like an electronic piece where you might take in one or more bits and it outputs some bits based on the inputs and the gate. So for example, the AND gate will output a 1 if both of the two input bits were also 1. Otherwise, it outputs a 0. The OR gate will output a 1 if one or more of the inputs were also 1. And the NOT gate, for example, only takes in 1 bit and it outputs the opposite bit. So if you give 0 to a NOT gate, it outputs a 1. And if you give a 1, it outputs a 0. And so people are actually able to build fairly complex circuits out of all these gates that can run all sorts of like crazy calculations. Okay, so we have a simple picture of like classical computing. Now, how does quantum computing differ from that? The big difference is that we get to use qubits, which no longer have to adhere to just one of some number of discrete states. In fact, a qubit is a continuous value. It's not just discrete. So a qubit is like a new mathematical entity separate than from just a bit. And that gives us a number of new properties that are awarded to us through like quantum mechanics. For example, qubits can be entangled, and I'll get to that at a later point in this video. So whenever I would try to search for like explanations on qubits on YouTube, I would always get an answer somewhat like this. Oh, a qubit can be in any state between 0 and 1 or something like that. And like that was always a really, really unsatisfying answer to me because, then what's the 0? What's the 1? How is this even represented? So I think I'm going to start there with explaining what a qubit is. So in quantum computing, when we're talking about a 0 or a 1 state, we're no longer dealing with like a single numerical discrete value, literally 0 or 1. When we talk about 0 or 1 in a quantum computing setting, we're talking about 2D vectors on a unit circle, basically. And so we're talking about these two vectors named 0 and 1, which one goes vertical, and that's 1, and one goes horizontal, and that's 0. And so together, these two vectors actually form what's known as a basis. And that just means that we can get to any point in two-dimensional space by adding up those two vectors in different proportions. So, for example, if you want to get to the point -3, 6, just multiply the horizontal vector by -3, multiply the vertical vector by 6, add those two together, and then you've gotten to the point -3, 6 by adding the different vectors inside your basis. So it's a very convenient little set of vectors we have here, and it's just two of them. So because we have a set of basis vectors, what we can actually do is we can represent any point on the surface of a circle, a unit circle specifically. And any point on the surface of that circle is pretty much represents like every possible value for a qubit. You can also extrapolate that out into a unit sphere, but I'm trying to keep things simple for right now, so we're not going to talk about the unit sphere, just the unit circle. So quantum computer scientists are talking about like values in between 0 and 1. If you look at that unit circle, you can kind of take the 0 vector and the 1 vector and you kind of rotate them in between each other or all around the circle, and that's what they're talking about, is we can have any continuous value on the surface of this circle right here. So I've been calling these vectors 0 and 1 this whole time, but in actual like mathematical notation, you'll see them written out kind of like this. So this is a bra and this is a ket, and together they are known as bracket notation, or I guess maybe braket. I don't know how you want to pronounce it. So if you have a vector which is like ket bra, then the vector is kind of like tall looking. If you have a vector that's braket, it's going to be like wider looking. They both hold the exact same information inside the vector, but the actual alignment, like which way is it facing, is going to come into play more when we're talking about like matrix multiplication, when we get into the actual like quantum logic gates. But for the most part, just you're going to be seeing ket bra. So our 0 vector actually looks like this, and our 1 vector is going to look like this. Okay, so measurement. I haven't mentioned this before, but another interesting thing about qubits is that we are never able to actually access their exact value. So we can know that they're like somewhere in between 0 and 1, but we will never know exactly where. Because the way for us large beings, I guess, I don't know, the way that we are actually able to look at the value of a qubit is we have to perform what's known as a measurement on it. And you perform a measurement with respect to some basis. So in this case, we're probably going to measure a qubit by 0 and 1, which means that you're going to take a qubit and it's going to collapse into either the 0 state or the 1 state, based on which state it is right now. And that's going to be a very probabilistic process. So let's assume, for example, your qubit is like directly in between 0 and 1. It's like perfectly in between. Then when you measure it, it has a 50% chance to go to 0 or 50% chance to go to 1. But it will go to either of the two, because you're measuring it based around that basis. And so if you want to know the exact probability for you to go to either basis state, there's two equations to help you figure that out. And so the first one is just the basic idea that you can represent any qubit state as the summation of different weights of your basis states. And we actually already knew that because since you have a basis, which is a bunch of vectors where you can get to any point in 2D space by adding up those vectors, that includes all the points on the surface of a unit circle, which means any possible qubit state. So we already know you can get to that by adding up your basis vectors. For example, if you were right in between 0 and 1, then it would be 1 over root 2, 0 plus 1 over root 2, 1. And I'll have some graphic up on the screen to help explain why that is. Now, the second equation determines how you would go from these coefficients on the basis vectors to get to the probability. So all you have to do is just square the probability and then, square the coefficient and then take the absolute value. Now, it might seem kind of redundant to take the absolute value after squaring it, but that's because sometimes your coefficients might have like an imaginary number in them. That's mostly used if you're sticking with like the 3D unit sphere model as opposed to just the unit circle. So again, we won't be touching that much in this video. Okay, so quantum gates, kind of like classical gates, they take in a number of qubits and they have to output the same number of qubits. And like regular gates, the outputs are going to be determined by the gate itself and also the inputs. Now, mathematically, we can actually represent quantum gates by just matrices. And if you want to see what the effect of a gate is on some input qubits, you basically just multiply the matrix by your input qubit vector. Because remember, qubits are just like vector values. So the identity gate looks like 1, 0, 0, 1, because then if you apply that to 0, the 0 vector, which is 1, 0, you still just get 1, 0. If you apply it to the 1 vector, which is 0, 1, you still get 0, 1. So boom, that's your identity gate right there. That's easy. It's supposed to do nothing. Your NOT gate looks like this, and then you have a couple of other gates for like single qubits. So we have a lot of different quantum gates. There's also a bunch of different sets of universal quantum gates, which you can use to build any gate based on just like 3 or 4 or something. That was one of the concepts I found a bit trickier in class. But anyway, I'm mostly going to talk about one gate, and that's my favorite, and it is the Hadamard quantum gate. So the Hadamard gate is pretty cool because you put in either like 0 or 1, and it outputs a state perfectly in between 0 or 1, but it still encodes for where it was before the gate. So if you pass a 0 into the Hadamard gate, you get what's called the plus vector. And that's what I was talking about before with measurement, is you get 1 over root 2, 0 plus 1 over root 2, 1. That's the plus vector. The minus vector, which is what happens if you pass a 1 into the Hadamard gate, that's 1 over root 2, 0 minus 1 over root 2, 1. And then if you pass either of those back into the Hadamard gate, then they kind of end up canceling out. And then you get back either 0 or 1, which is like really cool. Now, the cool thing about plus and minus is that since they are at a 90-degree angle to each other, they can also be used as a basis for 2D space. So if I wanted to, I could have done this whole video explaining quantum computing with like plus and minus as opposed to 0 and 1. But I didn't, because 0 and 1 is just like simpler, because they're not rotated like 45-degree angles. So, and also if you want to measure your qubits, you could also choose the plus minus basis to measure them, and you don't necessarily have to always choose 0 and 1. So when you have a quantum logic gate that takes in and then outputs more than 1 qubit, those 2 qubits become entangled. And entangled is just a fancy word for saying 1 qubit state, when it gets measured, is going to be determined by a different qubit state when it gets measured. And in order to illustrate this, I'm going to teach you all about the controlled NOT or C0 gate. So the C0 gate is pretty cool in that it takes in 2 qubits. So the first qubit can be whatever you want. The second qubit can also be whatever you want. But in the output, the second qubit gets flipped only if the first qubit is 1. So let's say we put in 2 qubits. Let's say we put in the plus qubit and the 0 qubit. So the plus qubit means that your first one is either a 1 or a 0 with equal probability, and your second qubit is a 0. So the resulting output state then for the 2 qubits is going to be you either have both of them are 0 or both of them are 1, because the first qubit is either a 0 or 1, and the second qubit is going to be swapped from 0 to a 1 if the first one is 1. So yeah, we're either going to get 2 zeros or 2 1s. The cool thing is they're also entangled. So if we go ahead and measure the first qubit in the 0, 1 basis, the first qubit's going to collapse into either 0 or 1. But because they're entangled, the second qubit will also automatically collapse without being measured. So if we measure the first qubit to be 0, the second qubit will always come out to be 0. There is no question about it because they're entangled. And if we had measured the first qubit to be 1, the second qubit would also always be 1, no questions asked. So that's pretty much entanglement. Ooh, okay, so before I get into an example of a quantum circuit, I'm going to explain matrix multiplication and a little friend known as the tensor product. Let's say you have like a bunch of quantum gates, maybe like a bunch of Hadamard gates, and you want to rig them to take in more than 1 qubit. The way generally that we would represent 2 or more qubit systems in math is not just like, oh, we have like two qubit values. Nah, you would use what's called the tensor product. So the tensor product is you have 2 vectors, or like 2 matrices basically. You take the second matrix and you multiply it by every single value inside the first matrix, resulting in a much larger matrix. If you want to represent the state for 2 qubits, you would use the tensor product on 2 qubits. So the value, so if let's say you have 2 qubits which are both 0, that's 1 0 and 1 0. So if you multiply the second 1 0 by every value in the first 1 0, you end up with 1 0 0 0. So that's a 4 by 1 matrix that represents a 2 qubit state where both qubits are in the 0 position. Now, if you had 2 1s, that's 0 1 0 1. So you have 0 0 0 1. Basically, it's kind of like counting on your fingers, where 2 zeros is like 1 0 0 0, and then you have for 0 1. You would have 0 1 0 0, and then 0 0 1 0, and then 0 0 0 1. That's how you can represent a system of 2 qubits. And you might want to do that, let's say if you have 2 qubits and you want to pass both of them into like a Hadamard gate, you can use a tensor product on the Hadamard gate, so that way it's 4 by 4 instead of just 2 by 2. And then you multiply that by your 4 by 1 matrix for a 2 qubit system, and then you get as output another 2 qubit system, but now both of them have passed through the Hadamard gates. And so that's how you would, change up the math for like larger systems of qubits and using different gates on like different qubits. So before we end the video, I want to show you all how to construct a basic quantum circuit. So let's say we want a perfectly random number generator that returns some number between 0 and 256 exclusive. I chose specifically 256 because that's like how many different values a single byte can hold, and that's 8 bits. So that's pretty much what we want, is just a random number, or a random byte value. So what we can do, we want this to be perfectly mathematically random. And the definition of mathematically random is every possible output needs to have the exact same probability of being returned. And that's actually really, really, really easy to do in quantum computing. All we have to do is get like 8 input qubits, all in the 0 state, pass each of them through a Hadamard gate, and then we just take a measurement of each of those qubits at the very end. Now, the interesting thing is that each of those 8 qubits would be entangled. But we're not doing any sort of like, oh, only apply the Hadamard gate if like the first qubit is 1 or whatever. It doesn't matter. Every qubit is going to be getting the Hadamard gate. So no matter whether the first qubit is 0 or 1, the second qubit is still plus, even after the first qubit was measured. So we can still measure it to be either 0 or 1 with equal probability. So by having 8 input qubits and 8 Hadamard gates, we get every single bit string of length 8 with equal probability. And therefore, that is the mathematical definition of perfectly random. So that is how we would build a random byte generator on like a quantum computer. Now, this is really, really, really easy to do on a quantum computer because it runs on probabilities. But most quantum algorithms that people have built, like all the useful ones, they actually need to give like a deterministic answer. And the way those work is they use some kind of like cleverness to always return qubit values where the state is very close to either 1 or 0, or maybe like plus or minus or some other basis. So that way when you go ahead and measure it, you're almost always going to get a deterministic answer. Maybe I'll try and explain like Shor's algorithm or something in a later video, but I think this video is long enough, so I'm going to go ahead and end it right here. Okay, well, that was a lot of information. So hopefully you got all that, or if you didn't, go watch the video again and like it and comment and subscribe. Yes. Yeah, this video was a lot of work to produce, but it was also a lot of fun. I'm very glad I don't have to like rely on knowing this for a grade anymore, but you know, I wouldn't mind doing like some videos or whatever on this in the future. But that's pretty much all I got for today, so thank you all so much for watching, and I will see you all next time.